Hello and welcome to this video on soil classification by ISSCS. ISSCS stands for Indian Standard Soil Classification System, which is a method of classifying soils based on their grain size, plasticity, and engineering properties. In this video, we will learn about the different types of soils according to ISSCS and how to identify them using simple tests. Soils are composed of solid particles of various sizes and shapes, which are held together by water and air. The size of the soil particles determines the physical and mechanical behavior of the soil, such as its permeability, compressibility, shear strength, and drainage. Therefore, it is important to classify soils according to their particle size distribution. According to ISSCS, soils are classified into 6 major groups: boulder, cobble, gravel, sand, silt, and clay. The table below shows the range of particle sizes for each group. Soil group particle size: boulder greater than 300, cobble 300 to 80, gravel 80 to 4.75, sand 4.75 to 0.075, silt 0.075 to 0.002, clay less than 0.002. The gravel and sand groups are further subdivided into coarse, medium, and fine subgroups based on their particle size ratios. The table below shows the subgroups and their symbols. Soil subgroup symbol particle size: coarse gravel GC 80 to 20, fine gravel GF 20 to 4.75, coarse sand SC 4.75 to 2, medium sand SM 2 to 0.425, fine sand SF 0.425 to 0.075. The silt and clay groups are also subdivided into low plasticity and high plasticity subgroups based on their liquid limit values. The liquid limit is the moisture content at which the soil changes from a plastic state to a liquid state when subjected to a small shear force. The table below shows the subgroups and their symbols. Soil subgroup symbol liquid limit, %. Silt with low plasticity ml less than 35. Silt with high plasticity mH greater than 35. Clay with low plasticity Cl less than 35. Clay with high plasticity CH greater than 35. To classify soils using ISSCS, we need to perform some simple tests on the soil samples. The first test is called sieving analysis, which is used to separate the soil particles into different size fractions using a set of sieves with different openings. The sieves are arranged in descending order of opening size from top to bottom, and the soil sample is placed on the top sieve and shaken for a specified time. The weight of soil retained on each sieve is recorded and used to calculate the percentage of soil passing through each sieve. The second test is called hydrometer analysis, which is used to determine the particle size distribution of fine-grained soils that cannot be separated by sieving. In this test, a soil sample is mixed with water and a dispersing agent in a glass cylinder and allowed to settle for a specified time. A hydrometer is inserted into the cylinder at different depths and times to measure the specific gravity of the soil-water suspension. The specific gravity values are used to calculate the percentage of soil finer than a given particle size. The third test is called Atterberg limits test, which is used to measure the plasticity characteristics of fine-grained soils. In this test, 3 limits are determined: liquid limit, LL, plastic limit, PL, and shrinkage limit, SL. The liquid limit is the moisture content at which the soil changes from a plastic state to a liquid state when subjected to a small shear force using a device called Casa Grande apparatus or cone penetrometer. The plastic limit is the moisture content at which the soil changes from a semi-solid state to a plastic state when rolled into threads of 3 mm diameter by hand. The shrinkage limit is the moisture content at which the soil changes from a solid state to a semi-solid state when dried in an oven. The fourth test is called consistency index test, which is used to measure the relative consistency or stiffness of fine-grained soils at a given moisture content. The consistency index, C, is defined as C equals LL, W, LL, PL, where W is the natural moisture content of the soil. The C ranges from 0 to 1 and indicates the degree of saturation of the soil. A higher C means a stiffer soil and a lower C means a softer soil. The fifth test is called activity test, which is used to measure the relative proportion of clay minerals in fine-grained soils. The activity, A, is defined as A equals pi, % clay, where pi is the plasticity index, pi equals LL, PL, and % clay is the percentage of soil finer than 0.002 mm. The A ranges from 0 to 3 and indicates the type of clay minerals present in the soil. A higher A means more active clay minerals such as montmorillonite, and a lower A means less active clay minerals such as kaolinite. The sixth test is called compaction test, which is used to measure the relationship between dry density and moisture content of soils when compacted by a specified amount of energy. The compaction test can be performed using two methods, standard Proctor test and modified Proctor test. In both methods, a soil sample is placed in a cylindrical mold and compacted by a hammer with a specified weight and number of blows. The weight and volume of the compacted soil are measured and used to calculate the dry density and moisture content. The process is repeated for different moisture contents until a maximum dry density is obtained. The curve obtained by plotting dry density versus moisture content is called compaction curve, and the point corresponding to the maximum dry density is called optimum moisture content, OMC. The seventh test is called shear strength test, which is used to measure the resistance of soils to shear failure when subjected to an applied stress. The shear strength test can be performed using different methods depending on the type of soil and loading conditions. Some of the common methods are direct shear test, triaxial compression test, unconfined compression test, vane shear test, and plate load test. In each method, a soil sample is placed in a device that applies a normal stress and a shear stress on the sample until it fails. The failure envelope obtained by plotting shear stress versus normal stress for different samples is called Mohr-Coulomb failure criterion, and the slope and intercept of the envelope are called angle of internal friction, phi, and cohesion copyright, respectively. These are some of the basic tests that are used to classify soils using ISSCS. By performing these tests, we can determine the properties and behavior of soils under different engineering situations, such as foundation design, earthwork construction, slope stability analysis, etc. We hope you enjoyed this video on soil classification by ISSCS. If you have any questions or comments, please leave them below. Thank you for watching and stay tuned for more videos on soil mechanics.